summarize. So you want to solve this ODE over the interval x sub naught b. Good. The first thing you do is pick a value of h or a value of n and figure out how many iterations you need. So your solution is going to look like this: x sub naught, y sub naught, x sub 1, y sub 1, and so on. And the y sub I plus first value is going to be the right side of the differential equation evaluated at x sub I, y sub I times h plus y sub I, okay? And you'll always know what, well, x sub I you'll always know, but y sub y will be estimated on the first step. I's are iteration, okay? Numerical analysis class, you have to write down I a lot. So i's are iteration. It starts at when I is 0, you're at the original point. When I is 1, you're at the first point, and so on. Okay. I'm sorry, when I is 0, you're at the first point, and so on. All right. All right, because the original point you have. Okay. Let's actually see what this looks like in application. So we're going to look at our IVP that we solved. We know the solution for this. We're going to try to solve this with Euler's method. I randomly pick an interval from 1 to 10 because the function doesn't exist at 0. If you're starting to the right of 0, that's not 1. You have to do a little bit of decimal. So I'm going to keep this simpler where I can. So I'm going to try to find the solution of this from 1 to 10. H equals 1. So H equals 1. X sub I, I'm going to have 10 iterations, right? 0, 1, 2, 3 to 9. This is the formula that determines the I sub first value of y. So if I is 0, you're starting at y sub 1. And then I know f is the right side of the differential equation. If the left side is just y prime. So it's x squared, so x sub I squared minus x sub I plus 1 minus 2 times y divided by x sub I times h times 1 plus y sub I. All right. We're going to solve this in Excel. All right, here we go. Let's go to Excel. Sorry. Okay, let's go to Excel. Here's our example, example 2. Okay, so I'm gonna do, I'm gonna do 0 to 9. So this is gonna be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Those are my values of x. My values of I, I'm going to make red, and we'll see what they are in a second. And then those are so this is where I'm going to store my y's. This is where I'm going to store my slopes, estimates of slopes. Now, numerically, you have to figure out the slope before you figure out the y, but I just wanted the x and the y's to be next to each other, so that's why I did that. All right, so now let's do, well, I know the first value of y, right? It's 0.5 or 1/2. Let's figure out the first slope. Okay, so for that, I wrote some code here already, so I don't have to come up with it in front of you here. All right, so the slope, if you remember, it was x squared. In this case, the first value of x is b2. So b2 squared minus x minus b2 plus 1 minus 2 times y. The first value of y is c2 divided by x. So I'm going to copy this. I'm going to paste it into here. And until you give an equal sign, Excel doesn't read that as a formula. So I'm going to give it an equal sign. So the first slope is 0. All right. And then what happens? So this is my first, this was given, right? So now I'm going to use the previous steps to figure out y sub 1. So y sub 1 is going to be equal to the previous y plus h, which is 1, times the slope evaluated at the previous x and previous y. So this. All right. I'm going to drag this down. I'm going to drag this down. All right. Here's my estimates. I used numerical analysis to estimate this. All right. So the question is, how close are we? And what I'm going to do is I'm going to go to Desmos. Okay. So here's my original function, and you know what? Let's let's do it between 0, what did we say, 0 greater than 0, and then we said it's 10, right? Okay, so here's, yeah, it's alright, just greater than 0. Okay, so here's my original function, and here's my points, right? 0.5, 1.5, 2.83. So I'm going to plot the points against the true solution that I know to see how close I am. I'm going to plot them in red. You ready? All right, here we go. Plot. Hey, they're pretty close. The only place where something, and then they're pretty close. Good. The only place where something weird happened, if I zoom in, is right here, because you have a turn here. It told us that the derivative at the point 1.5 was 0 because the function has a minimum here. So the fact that the derivative is 0 means there's a flat tangent line, and that tangent line threw you off the curve a little bit. But then it recovered again. So as we'll see later on, with the places where the function has turns is where sometimes Euler's method doesn't survive. Well, in this case, the turn wasn't that dramatic, and we started at a turn. We didn't start before. So in this case, it wasn't that bad. All right, let's summarize our results. All right, so here's my results, x sub I, y sub 1, and then here they are plotted against the true solution. All right, good. Not bad. All right, we want some sort of a way to think about errors. So analyzing error is important. Actually, it's probably the most important part, because if you're doing any sort of estimation or prediction, the error is just as important as your estimation, right? Because otherwise, I mean, you can just sit there and predict whatever you want. Okay. Or estimate whatever you want. Okay. So, let's say y of x is my true solution. This is Euler's method. So, you've seen this formulation before. The error at each step, I'm going to call it E sub I or error sub I. It's going to be y evaluated at the x value. So the true value minus the estimated value of y. The question is, if I don't know the true value of y, how can I find the error? Well, we've encountered this twice before in our course. In the statistics part, you can't evaluate the error exactly, but you can put a bound on the error, and you can know how to make the error smaller, okay? And then that is a very sophisticated topic. That's why it's part of the reason why numerical analysis courses are grad courses. But for now, we got to start talking about error somewhere. So for us, error will be the difference between the true value and the estimated value. This is a learning environment. Okay. There's two sources of error when you apply numerical methods to solve IVP. The first source of error comes from the fact that you're using a tangent line at one point to estimate the other point that's away from it. So when I zoomed in, I kind of showed you how that might happen. It throws you off the curve. The second source of error is round-off errors, because obviously computers truncate values. And I actually don't know how to, I don't know how to analyze round-off error. I think that's more of a computer science topics, but those will be the two sources of errors. We'll focus on the truncation errors. All right, so I'm going to calculate the error for my, first numerical method. I'm going to call the last column, you know what, let's make this 16 and bold. I'm going to call my last column error sub I. What is an error? Do you remember what the true solution is? 1/4 x squared minus 1/3 x plus this plus this. Okay. So, this is the true solution. I just wrote the code here. 1/4 0.25 times x squared minus minus 1/3 times x or times b2 plus 0.5 plus 1 divided by 1 over 12 times x squared. All right, so I'm gonna write that in here, and then what I'm gonna do is I'm going to subtract from it. I'm going to put parentheses around the true value. I'm going to subtract from it C2. I'm going to subtract from it C2 the estimated value. Okay, so I'm going to write an equal sign here. Okay, so just All right, these are my errors. Now, sometimes some errors will be positive, some errors will be negative. So what I'm going to do is I'm going to take the absolute value of the whole thing. The absolute value of the whole thing. And in this case, it doesn't matter, but just for future references. Okay, and let's figure out the average of the errors. The average of the errors is 0.47. Okay, good. I don't know. You have to compare them to each other to know what they mean, but it looks like it's a pretty good fit. All right, so let's summarize our results here. Here's the errors, 0.47. Okay, and then here's the graph. All right, so